I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll explore what logarithmic functions are. Let us first recall exponential functions, explore how to solve them, discover inverse function which is logarithmic, then explore logarithmic functions and extend our knowledge. So here is a lesson with the student Abhinav, a grade 8 student doing grade 11 mathematics. Our approach, engaging minds, help us to perform much better. We can now connect to context, visualize strategy, apply learnings, and bridge the gaps. Engaging minds help in creative thinking and problem solving. Gain the confidence. Get ready for future. We develop both mathematical and social skills. I can be part of your success story. Build strong foundation and ensure bright future. That is the gift of education. You can always contact me on the email address given. Join my classes. Let us now learn with Abhinav. Hi Abhinav, how are you doing?
I'm good. How are you?
Very good, very good. So Abhinav, today what do you want to do?
Like a review on exponential functions and an introduction on logs.
Sure. So, review on exponential functions means you know all about exponential functions, correct?
Yeah.
Very good. So, I'll kind of connect with exponential functions and logarithms. You know, they are kind of related. And
Yeah.
let's see how they are related and how to work with them. Let me share with you a whiteboard.
Okay.
Can you see the scheme?
Yeah.
Good. So, now we'll take basic exponential function, which is 2 to the power of x. And we'll also graph it. So let me take this function 2 to the power of x. Let's say y is 2 to the power of x. So we'll put some values of x and try to graph it. Can you tell me what are the key values which I should consider?
The asymptote.
Okay. So what is the asymptote?
2.
No. In exponential functions, we have a horizontal asymptote, which is y equals to 0. Exponential functions are always positive, right? They approach 0 when x is approaching negative infinity. That means like we are having 2 to the power of minus infinity kind of a thing. Do you understand?
Yeah.
So when you divide by a very large number, but it is positive, you actually approach 0, right? So this is what it means. You understand?
Yeah.
So this is the horizontal asymptote which you are approaching. Now, the key points which are always of our interest will be for x equals to 0, for example. So what is 2 to the power of 0 equals to?
1.
That is always 1. Anything to the power of 0 is always 1. So at the origin 0, if x is 0, then y-intercept is going to be 1, correct? Let me just
Yeah.
make it bigger here. 1. Is that clear? 1.
Yeah.
Now if I take this value as 1, then it is 2 to the power of 1, which is 2, correct? So at 1, I have 2. Correct?
Yeah.
If it is 2, then 2 to the power of 2 is 4, and so it goes way beyond. But if it is minus 1, then 2 to the power of minus 1 is half, correct? So
Yeah.
it comes to this particular point somewhere here. Connecting these points, we kind of get the exponential graph. Is that clear to you?
Yeah.
So that is my exponential graph for 2 to the power of x. If I have 3 to the power of x, then how will my graph change? Can you tell me?
It'll get wider.
3 to the power of x, not necessarily wider. At 1, what will happen to this point? It will go at 3, right?
Yes, it'll be more like
Steeper, right,
condensed.
here on this side. But
Yeah.
at -1, what is going to happen? It
Then
is
it's
going to
gonna
be smaller.
yeah.
So the graph will be like this. Do you understand the graph now?
Yeah.
So on this side, it will be above, and on the left side, it will be below the graph of 2 to the power of x, and this is 3 to the power of x. Is that clear to you?
Yeah, it's clear.
So at 1, the value will be the base value. Correct? Now, on this function, exponential function, what are the restrictions on x? Are there any restrictions on x? X actually belongs to all real numbers. There are no restrictions, correct?
Yeah.
But if I write a general equation, y equals to some base to the power of x, then there are some restrictions on base b. What are the restrictions on the base? Tell me.
It can't be a negative number.
So it is greater than 0. Can
Yeah.
it be 0? No. It has to be greater than 0, right?
Yeah.
And what else? Can it be 1?
No,
Why it cannot be 1?
because then it would just be like a straight line. Because 1 to the power of anything is 1.
It is not a growth. It is not exponential. It is a horizontal line. That is. Is it okay?
Yeah.
You can put it 1, but it is not an exponential function. So for that function to be exponential, b has to be greater than 0 and not equal to 1. Is that clear to you?
Yeah.
Perfect. Now, another thing which we figure out is that when x approaches infinitely large, then y also approaches infinitely large value. Okay, all this is done. Now the problem comes, let me go to a, we have got all this, right? So
Yeah.
if I say 2 to the power of 1 is 2, 2 to the power of 2 is 4, but if I have to solve a question which is 2 to the power of x is 3, how will I solve this question? What is the value of x which will give me 3 here? How will I solve this question?
It would square root both sides by
Square
x.
root will not give me. Square root is inverse of square. So 2 to the power of x is exponential function. There is no square in it. It is not x squared. Correct?
Yeah.
So that's the big issue. So let's get to a new page. So as you were saying, if I have x squared equals to, let us say, some number 8, right? Knowing that x is greater than equal to 0 for our condition, in that case, x is equal to square root of 8, correct?
Yeah.
Because inverse of square is square root. Correct. Now my question is changed. I'm saying 2 to the power of x is 3. Let's take this later. Let us say 2 to the power of x is 8. Then what is x equals to?
3.
3. How could you figure it? Because 8 is 2 to the power of 3, and then you have common base. And so exponent should be same, right?
Yeah.
I say exponents are equal. That was perfect. Let's move forward. 2 to the power of x, let us make it 5 this time. We want to find x. We know 2 to the power of 0 is equal to 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. Oh, where is 5? Somewhere in between. How do I get this answer? This is very difficult to figure out.
Yeah.
Simply because we do not have inverse of this function, right?
Yeah.
Now this inverse is the logarithmic function. So logarithm is inverse of exponential function. Is that clear to you?
Yeah.
So you can use the log table. You can do the log operation on both sides and get the answer. We will see how. But first thing first, we have understood that log is our solution, and therefore we are studying log today. Is it okay?
Mhm.
Let us do this graphically. We have 2 to the power of x. Let's say y is equals to 2 to the power of x. Okay. Let me just draw this curve in a green color. You know how to draw it, correct?
Yeah.
If I write this point as 1, and if I write add 1, 2, I know this graph is 2 to the power of x, right?
Yeah.
Now this is perfectly 2 to the power of x. So these 3 points really define my graph y equals to 2 to the power of x. Now, uh, the idea is to find the logarithms. Logarithm is inverse. How do you sketch inverse of this function? You could graphically reflect it on a line which is y equals to x, right?
Yeah.
So if you reflect on the line, then what happens? The points swap.
Yeah.
0, 1 becomes 1, 0, correct?
Yeah.
1, 2 becomes 2, 1. I mean, 1, 2 becomes 2, 1. So at 2, we have now 1, correct?
Yeah.
And the point which is minus 1 half becomes half minus 1. So we do get a graph which is kind of like this, right?
Yeah.
Where instead of horizontal asymptote, which we had earlier, now we have a vertical asymptote, correct?
Yeah.
So the scenario changes. So what we see really is that the coordinate points which were 0, 1, 1, 2, minus 1 half, now switched to half minus 1, 1, 0, 2, 1, correct? And also, we had the horizontal asymptote which shifted to now a vertical asymptote. Do you see that?
Yeah.
So that horizontal asymptote was y equals to 0. Now we have x equals to 0, right? Vertical asymptote, which is x equals to 0, right? Earlier it was y equals to 0. So it's swap. Also, you notice that if you look into the domain and range, so x domain was what? Domain earlier was x belongs to real numbers, and the range was y greater than 0, correct?
Yeah.
Now, for the inverse function, let me write down here log, and this is exponential. This swaps, correct? So the domain x is now greater than 0, and the range y belongs to real numbers. You see that?
Yeah.
It makes sense because we have a vertical asymptote x equals to 0, which the graph is approaching. It is on the quadrant on the right hand side of this axis. It is in quadrant 4 and 1. The x value can be only greater than 0, but the y values could be any real number as shown in the graph itself. You get the idea.
Yeah.
So we have the logarithmic function which is inverse, and now if I have to figure out what is let us say value at 3, let us say value at 3, then basically I could go back on this graph and get the value. Is it clear to you?
Yeah.
Let's now see how to do all this. Okay. So we have understood one. Okay. In calculator, you find log written as log x and ln x. Because we are going to use calculator to begin with, so let's understand these. So here the base is 10, here the base is e. This is default. If nothing is mentioned, you know it is base 10.
Okay.
Let's look into base 10. It's very easy to understand. So what is 10 to the power of 0 equals to? 1.
1.
10. Oh. 10 to the power of 3 is 1000. So number of zeros in 10 will give you all this, correct?
Yeah.
So what you understand here is that the base is 10. So we are saying 10 to the power of n will give me a number which is, okay, let's keep it a number 6, 1 million. Now the inverse function will be, basically what I'm saying is, this is x, right?
Yeah.
So if it is 6, then our answer in exponential function is 1 million. In logarithmic function, that becomes million becomes the x value, right? And that becomes the y value. So we are saying log and the base is 10 of 1 million, which is 10 to the power of 6, is equal to 6. Do you see this part?
Yeah.
Log to the base 10, 10 to the power 6 is 6. Oh, just the exponent, right? Let's look into this in more details. So that means log to the base 10 of 100 is how much?
2.
Very good. Log to the base 10 of 100 is 2 because 10 to the power of 2 is 100. Because 10 to the power of 2 is 100. Therefore, log to the base 10 of 100 is 2. So that is what the inverse function is. Correct?
Yeah.
So how did you get it? Let's look into it again. Log to the base 10 of, let us 1000 is 3, right?
Yeah.
How do we know? Because see, because 1000 is equal to 10 to the power of 3. That is why. Because it is the reverse of exponent, right? Do you see
Yeah.
this? What did we do? We maintained the same base. We maintained the same base 10. Do you see that? And exponent changed.
Okay, what if log was like power to like the 7? Would it be power to 7 then?
Yeah. So log to the base 10 of 10 to the power of 7 will be 7.
Okay.
Because I could write this in exponential form. Exponential form is 10 to the power of 7, right? If I take it this side, so it is 10 to the power of 7 equals to 10 to the power of 7. It makes sense, correct?
Yeah.
So what we are trying to say here is log to the base 10 of 10,000. We don't know. We say why? We say we don't know. Log to the base 10 of 10,000 we don't know. So we say let it be y, correct?
Yeah.
Let it be y. So then how are we solving this equation? Then we say, well, that means if I write this in exponential form, I get 10,000 equals to 10 to the power of y. Correct?
Yeah.
Now I say, what power of y will give me 10,000? You say, oh, it is 10 to the power of 4. That means y is equal to 4. Is that clear to you? So
Yeah.
we actually solved this equation. Correct?
Yeah.
We solved this equation. We didn't know, let us say we don't know what y is. We say this. Okay, very good. So so this part is correct. Now let's go back to our equation. We say, now, if I say, how can I write 10 to the power of 4 equals to 1000 in logarithmic equation? Let's go back. Let's say 10 to the power of 4 equals to 10,000. This is exponential, write in log. You know the base is 10,
Yeah.
and that is the result, 4, right?
Yeah.
So we say log to the base 10 of this number, which is 10,000, is equal to. Now we are saying 2 to the power of x is, let's say, 5. How will I write it in log?
Log to the base of 2,
Of 5?
5 equals x.
That is correct. So I now know how do we write from exponential to log and from log to exponential, correct? Now it is only, now we know, we can calculate log to the base 2 of 5 using
Yeah.
some technique, correct? But now actually we know that x is log to the base 2 of 5. That is the exact value, correct?
Yeah.
So that is kind of relation between exponential and logarithmic functions, and we do get the same thing. I mean, we can solve exponential equations. So now you understand, you can solve exponential equations using log. Perfect?
Yeah.
Now, finding inverse is also swapping x and y. So if I write 2 to the power of x is 8, this is exponential equation. So if I have to write in logarithmic equation, I will write log to the base 2 of 8 is x. Correct?
Yeah.
So that is changing this. Now let us say we have an equation which is y equals to 2 to the power of x. How will you find inverse of this function?
Log base 2 y equals x.
Or you could also say x is equals to 2 to the power of y. This relation also is an inverse relation because you swap x and y, correct?
Okay.
Correct. So one way of writing an inverse function is this, of course, and the other way of writing the inverse function is log to the base 2 of y is x. Is it okay? So
Yeah.
both are inverse functions of y equals to 2 to the power of x. Now the first one, of course, is called logarithmic equation in inverse. This is exponential form, and this one is log form. Correct? So that is how you are going to relate the two. Now let's try to solve some simple questions using calculator, and we have log to the base 10 in the calculator. So if I say log, can you find what is log of 5.2?
0.716.
Pardon?
0.716.
So it is less than 1. Log of 12.
1.079.
1 point?
079.
Slightly more than 10 because log of 10 will be 1, correct?
Yeah.
Correct. Now my question is, log to the base 10 of some number a is negative 0.5. So what is a?
So it's a to the power of negative 0.5 because a is the base, right?
A is not the base, 10 is the base.
Oh,
What is a?
okay. Zero point 316.
So you said a is 10 to the power of minus 0.5, correct?
Yeah.
How much did you get?
0.316.
Got it? So
Yeah.
you could now actually, if I know that log of something is some number, we can find what, right?
Yeah.
Can you check your result? Log of 0.316 is how much?
Okay. Negative 0.50.
Correct. Very close. So that is correct, right? So approximate answers, we got just the right thing. Correct.
Yeah.
So now you understand how do we work with log both ways, correct? Now, let's go to some questions based on this. Log to the base 2, let's take, right? Let's take 2. So log to the base 2 of 16 should be equal to what?
Uh, 4.
4 is correct. So if it is not known to you, you will say let it be y or some number. Then you say 16 equals to 2 to the power of y, correct?
Yeah.
And you know 16 is 2 to the power of 4 and 2 to the power of y gives you 4 equals to y, correct? That is
Yeah.
one way of doing it. Other way you could have done like this. You could have written the question as log of to the base 2. Instead of 16, we could write 2 to the power of 4, correct?
Yeah.
And since this part is 1, since this part is 1, we know it is, you remember 10 to the power of 2 was 2, right? Answer.
Yeah.
So now this should be equal to 4, correct?
Yeah.
So we have, in a way, learned a rule that if I have log to the base b of b to the power of x, then the answer is x. Is that correct?
Yeah.
So we have learned this rule from all these experiments which we have done. In the next class, we'll actually derive and prove this using exponential equations. But today, with trial and error and all these things, we have learned this, correct?
Yeah.
Let's try to connect our learnings and figure out some more questions. So let's do log to the base 2 of, let us say, 1024. Log to the base 2 of 1024. How much is this equal to? Let's say we don't know. Let's say a. So this is 2 to the power of a. On this side, we know 2 to the power of 10 is 1024. Or you could write this as now. When you're doing logarithms or exponential functions, you should know powers of 2, 3, and some numbers. You understand?
Yeah.
It is always good because very handy. So 2 powers, 2 to the power of 10 is kilobytes. and the actual number is 1024. So close to 1000, slightly more, right? You understand bytes, right? In which all the computer memory is measured.
Yeah.
So the value is 2 to the power, is a binary system. So we have 2. Power of 10 gives you a number very close to 1000. It's called kilobytes. 1024, you should remember. Is that okay? Now that helps because it helps you to find the answer for questions like what is log to the base 2 of 256, right? 512, because these are all fractions of 1024.
Yeah.
So you can easily relate to powers of 2 and get your answer. Correct. Now tell me, log to the base of square root of 2 of 8 is how much?
Four.
How did you do it?
Because 2 times 2 times 2 is 8, but it's square root of 2. So we have to do it one more time.
So you wrote 8 as 2 cube, right?
Yeah.
But you want this base and the number 2 should be same. So I will have to write this as log of square root of 2. So since I'm doing square root of 2, I have to square it, right? Times 2, and it is already 3 here. Do you see that? So basically, this is square root of 2. So basically, it is equal to log of square root of 2, and that is 6. Do you see that? Square root of 2 to the power of 3 times 2, 6. So your answer should have been 6.
Okay.
You get the idea?
Yeah.
8 is 2 cube, and that is square root means half. So half times 3 is 6.
Okay.
I mean, double, right?
Yeah.
3. 3 times 2, I should say. So that is how we could see now the relation. If I change the base to some other number, how do I relate it without doing change of base formula? Very important, correct? We are not doing change of base formula, but we are learning how to use change of base, correct?
Yeah.
So today's class is more conceptual based. We're trying to learn the concepts. We'll get into these details soon. Don't worry. Next class will be like far ahead, but we are already ahead of many things. So now let's see. Log of 3 of 27 is how much?
3.
So log of 27 of 3 is how much?
-3.
Okay, how you're not quite right, but okay, how should we do it? So basically, we have to write 3 in terms of 27, right? So how is 3 related with 27? 27 cube root is 3, correct?
Yeah.
I could have replaced this 3 with 27 cube root. So I get 1 over 3 as my answer, not minus 3. 1 over 3. You get the idea?
Yeah.
1 over 3, right? So you're close, but that is how you have to see. See, log to the base 3 of 27 is 3, but when I interchange the base and the argument, it becomes 1 over 3.
Yeah.
Understood?
Yeah.
Important thing to visualize. Okay, let's see. Log to the base 5 of 25, or okay, you know, the 125 is how much?
3.
So now log to the base of 125 of 5 is how much?
1 over 3.
Correct? You understand now this logic, correct? So what we are saying is formula, for another formula, log to the base a of b is equal to 1 over log to the base b of a. Done. Do you see this part?
Yeah.
We learn this in after third chapter on logarithms. This is called this is application of change of base formula.
Okay.
We have understood this concept even without knowing the basic logarithmic rules, correct? Do you
Yeah.
see that idea? So, so the concept which you have learned just now in your very first class on logarithms is huge. Since you have connected with a couple of things. One, you understood that log to the base a of b is equals to 1 over log to the base b of a. Correct? You
Yeah.
have also understood that if log base of a is equal to, let us say 5, then log a of b will be 1 over 5,
Yeah.
right? So that is how you're trying to relate them. And so you know that log 2 of 8 is 3. So that means log 8 of 2 is 1 over 3. Correct? Applying these things, correct?
Yeah.
Very good. Now let's get to more details, right? Log to square root of 2 of of 1024 is how much?
12.
Correct. How 12? Log to the base square root 2. 1024 I wrote 2 to the power of 10, correct?
Yeah.
But we want this half. So we get log square root 2 of 2 to the power of, we want it to be half, right? So we'll do half times 2. Is it okay?
Yeah.
So basically, it is equals to log to the base square root 2 of square root 2 to the power of 20. So the answer should be 20, correct?
Okay.
Got the idea? So
Yeah.
try to relate them like this. Fine? Let's cube root. Log cube root of 2 to, let's say, 512 is what? Tell me.
27.
Huh?
27.
Let's check. Log cube root of 2. 512 can be written as 2 to the power of 9, correct?
Yeah.
Now you change that to cube root means 1/3 and third, right? So you write cube root of 2 and then cube it. That is 2 for me, right?
Yeah.
And then 9 it. I mean exponent 9, which is 27.
Yeah.
You are right. So you see now that cube root thing 1 over 3 actually multiplies when it goes up,
Yeah.
because that portion which we are taking as the argument, it is becoming that much smaller. Correct?
Yeah.
So you have understood this concept?
Yeah.
So we have related uh, logarithms with exponential functions. I like to bring you back to exponential functions just to, you know, uh, learn more about them. Now, when if I have an exponential function, what is the first difference? Let's say 2 to the power of x. So if I make a table, let us say the values of x are taken as, let's start with 0, 1, 2, 3, 4. Then 2 to the power of 0 is 1.
1.
2 square is 4, 8, 16. Correct?
Yeah.
So now what is happening? What is the first difference? 2 minus 1 is 1, 2, 4, 8. So we say the first difference is being multiplied by a constant factor. Is it okay?
Yeah.
It is a multiple. So first difference is a multiple. So when we talked about linear equations, first difference was constant.
Yeah.
When you talk about quadratic equations, second difference was constant. Any polynomial n degree, nth difference is constant. But for exponential functions, they are always multiple. So that means that exponential function really means it multiplies on existing number.
Okay.
Now we have to relate this to real life situation. Can you provide me examples?
Mm.
Where the thing multiplies based on what you have.
Yeah. Like number of bacteria.
Number of bacteria, very good. So, number of bacteria. Use a double every 2 hours, for example, correct? You could say
Yeah.
bacteria. Any other example? So, that is exponential growth.
Yeah.
Yeah.
Uh, radioactivity or like decaying matter.
Decay in matter. Radioactive. Very good. What else? Financial application.
Uh, interest.
Compound interest.
Yeah.
A simple interest is algebraic linear equation, right?
Yeah.
Because in simple interest, you are getting interest on what you invested, not on the present value of what you have.
Yeah.
Now, that gives you a very good difference. So as soon as you look into interest part, you get this idea that, let us say the growth rate is, let's say, 5%, right? So you have a curve which is kind of money is here and it goes like this, right? And let's say this is at the rate of 5%. Now, what really happens is that if you invest here, it becomes 5% on exponential functions. You do not get interest on this alone. You get interest on this also, which you earn. Do you see that? Interest on interest.
Yeah.
So this value, instead of being on that line, it goes slightly up. Do you understand? It goes slightly up above the line. Do you see that?
Yeah.
Next time, that also accumulates. So we have an exponential graph which is going way beyond the normal linear graph. So the exponential growth is a very, very fast growth
Yeah.
based on number itself. Right? So, for example, let's end this class with this example. We have a
Okay.
chessboard, right?
Yeah.
So on a chessboard, we have 8 times 8 columns, correct?
Yeah.
Okay. So one, we can just divide with 8 by 8. So if I put $1 here, and if I double it in every column, subsequently, then your project is total amount.
Yeah.
On the board. And also the last amount. So, can you tell me what is going to be the final amount? Let's draw it. 1, 2, 3, 4, 5, 6, 7. We'll stop. Now, so this is 1, 2, 3, 4, 5, 6, 7, 8, right? So we put $1 here, 2 here, 4 here, 8 here, 16 here, 32 here, 64 here, and 128, correct?
Yeah.
So this is the 8th position, and this is 2 to the power of 0. Do you see that 2 to the 0 comes first? 2 to the power of 1, 2 to the power of 2, right? So 2 to the power of 3. But this is the 4th position.
Yeah, so it's -1.
-1. So this box will be 2 to the power of, not 64, 64 minus 1. This is what I wanted to do.
Yeah.
Because each time thereafter, you are only placing it 63 times thereafter, correct? You started with 2. Got the idea?
Yeah.
So you have to be careful. So now we have figured out the last number. Now what you have to figure out is what is the sum of this series? 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus so on till 2 to the power of 63. There are 64 terms, of course. This is your exercise to do. How will you do this exercise? So let me make a fresh page to give you this problem. So we have to find sum of 64 numbers which start with 2 to the power of 0 plus 1 plus 2 plus. Tell me, how will you find sum of this series?
Uh, Find the number in each row and then add them all up.
Okay, I'll show you a technique. Let us multiply this series by 2. So we get 2 times sum of 64 terms is how much? So 2 to the power of 0, when you multiply by 2, you get 2 to the power of 1, right?
Yeah.
Your series now becomes this. Is that correct? Because you multiplied by 2, correct?
Yeah.
Now you subtract from this the previous series. So we have 2 sum 64 minus sum of 64 is how much? So when you subtract, all these middle terms cancel. You get 2 to the power of 0 minus, 2 to the power of 64, because that is my first thing, minus 2 to the power of 0, correct?
Yeah.
So this is how much on the left side? Left side is sum of 64 terms, right?
Yeah.
And so this was twice the number, and we have our answer 2 to the power of 64 minus 1. You see how we calculated the sum of the series, correct? So in exponential series, we could do all this and get our sum also. This reminds you of geometric series. Do you remember geometric? Did you do geometric series?
No.
Not yet. Okay, that's fine. So they are similar. So geometric series, you're multiplying a number by a fixed number to get the next number. Right. So in geometric series, if A is my first term, then second term is AR, then we are multiplying by R. So, so all these exponential functions which we saw today and also related with some examples, they kind of give you an idea of geometric sequences and series. So the terms when we take is called a sequence, sum when we take is called a series. Is it okay?
Yeah.
So it was necessary for me to connect exponential functions with a series and with logarithmic functions. You know why? A test examination question is going to connect them all. You get the idea?
Yeah.
So what we did was today, we learned about exponential functions. And we figured out that these are having an inverse, which is called logarithmic functions. And these are also related with geometric series. And we have so many applications related to exponential growth or decay, right? So, and in this exponential growth and decay, we had many examples which are real life situations, correct?
Yeah.
Even a cup of coffee on your table, when it starts cooling, it cools exponentially because more the difference between the room temperature and the coffee, faster it cools, correct?
Yeah.
Lesser the difference becomes, less. Get the idea?
Yeah.
So many natural things follow this exponential pattern. And therefore, it becomes extremely important for us to model these situations. And so we can model all these situations. While we model them, we have to also look into the series part because we are also interested in finding what the number is going to be after some time, correct?
Yeah.
Or how much investment has been done or how much growth has taken place. So, in all what we have gone through, is it clear to you?
Yeah.
So, this becomes a very, very important topic which relates to so many different things. And I hope now the concept should be very clear, right?
Yeah.
So, we can take many examples and see how logarithms will help us solve those exponential equations. Now, we have all these equations. How to solve them is key. Logarithms. You get the idea? So we'll begin with logarithms applications in the next class. Is it okay?
Yep.
Okay. So I'm going to end the session here, but I'd like you to summarize today's learning. So can you summarize what we have learned today?
So we reviewed on exponential functions and what they are and how we can graph them and how we can find the different points and asymptotes. And then we learned the inverse of an exponential function, which is a logarithmic function, which has a vertical asymptote instead of a horizontal asymptote. And you can use it to solve questions for exponential functions like 2 to the power of x equals 5. You can rewrite that as a log and solve for it. And then we did some real life examples, such as a chessboard.
Yes. Good. So keep it up. We'll continue from here. Keep sharing. Okay. Thank you. Have a great
Bye.
day.